Hello everybody. We've been discussing about cascade control for some time, and here we've been talking about two different kinds of control systems. One is a primary controller, another one is a secondary controller. The question that is before you is why do we need to have two different kinds of controller? The question is whether one controller, whether it is not sufficient. Why do we need to have two? Okay, so we address this question in terms of identifying a variable called a disturbance variable. A disturbance variable dynamic should be much faster than the primary loop dynamics. Okay, so that's what we discussed. I hope you can recall that. So if the secondary loop dynamics is much faster than the primary loop dynamics, we can go in for a kind of control mechanism called cascade control mechanism. So the secondary variable, the secondary controller will take care of the effect of the secondary variable over the primary variable in advance. Okay, so it will try to nullify the effect of that over the process variable in advance. Thereby, it will help the primary process to maintain the temperature at the desired temperature or the desired set point value. So thereby, it can ensure effective control mechanisms. Okay, so that's what we learned. Now let us move ahead and try to discuss something related to feed-forward controllers. So can you recall why do we need to go in for a feed-forward control mechanism? So the idea what I told you was very clear. Okay, so we have a disturbance and we know the model of the disturbance, how it is going to affect the process. Okay, so there is a prediction model available for us which can help us to predict exactly what is the impact of the disturbance over the process. So if you know that in advance, what you can do, if you know something in advance, you can always take preventive control actions in advance. So naturally, here also we are going to use a process a disturbance model, and we'll be designing something called a feed-forward controller, which will take a predictive or an advanced control. More I can say it is an anticipatory control action it can take in advance. Thereby, it can completely eliminate the effect of disturbance over the process output. So that's what we discussed. So the next important concept that we have been discussing is Smith predictor controller. Here I am showing you a process. We have a kind of a paper machine process. Here we are interested in measuring the thickness of the paper with the help of an optical thickness gauge, and once we measure it, we would like to control it. Okay, or whenever we talk about measurement, we should think always in terms of how to control it. So once we measure the corresponding thickness with the help of a controller, here in this case the controller is acting over a piston. Okay, so this piston will press this roller and thereby it will maintain the thickness of the paper. And here there is one important point in fact we should note here is there is a dead time associated here, because as soon as you measure the thickness with the help of a controller, when you're going to take corrective action, always the corrective action will be felt over the paper, okay, only after some time. So this time you normally call it as dead time of the process. So this dead time normally deteriorates the performance of the controller. So it's essential for us to design some mechanisms with the help of a mathematical model to eliminate the effect of this kind of dead time over the processor. So that's where in fact the idea of a Smith predictor really comes into picture. So here if you can notice here, in the real world process you cannot exclude a dead time from the process. So what we can do, so the only idea that we can imagine is why can't we employ a computer here, employ a mathematical model, use a computer to simulate it and try to eliminate the effect of dead time. That's always possible. So mathematical, that's what in fact Smith did by 1960. Okay, so he employed a mathematical model and then he ran that model in the form of a simulation in a computer parallelly along with the process, and then with the help of a kind of decoupling mechanism wherein he eliminated the effect of dead time, and thereby he could have obtained the predicted process variable. Okay, so if you notice this diagram very carefully, you can see there are disturbances acting over the process and there is an actual process variable here, and then once with the help of a process model coupled with the dead time, you can always obtain the corresponding disturbance free process variable output here. So the actual process variable subtracted from the disturbance process free process variable can always give you a good estimate about the disturbances, and this estimated disturbances when coupled with the predicted process variable can give you a dead time free kind of a variable that can be given to the controller. So here if you can notice clearly, with the help of a mathematical model, in fact we are decoupling the effect of dead time over the process, and thereby you are taking corrective control actions, and thereby you are also ensuring the appropriate performance of the control systems. So if you notice this diagram also, clearly you can see the estimated disturbances are happening over here, and the model gain and the time constants are put up everything, you are putting it everything inside this block, and then here you are measuring the predicted process variable with the disturbances, and then with the help of a controller you are controlling it. Clearly you can see that model dead time is decoupled here. So if you look at the corresponding modified version of a Smith predictor, something like this you can notice. So here C1 is the variable that you are interested in. This variable is not influenced by the dead time. So naturally you can take corrective control action, and thereby you can ensure the process output is maintained at a desired set point. So if you look at the internal model kind of a control mechanism, which is a slightly modified version of the Smith predictor controller, you can notice here that the model is there. So the model can have dead time. Sometimes you may not be having dead time also. So the IMC controller normally is a generalized version of a Smith predictor controller, wherein you are taking into account both the dead time as well as a process without dead time also. So here is the load disturbances that are going to act over the process, and C is the controlled output that in fact most of you are sure about. So the first stage of this process, if you can notice here, if you look at the previous diagram, very clearly you could have noticed that the process output is given to a mathematical model. So here is a mathematical model, and there is a positive feedback happening over here, and we can employ a very basic block diagram based representation for this, and you can get a reduced block diagram representation for the control system here. So you got GI by 1 minus GI into GM can fetch you the corresponding controller action, and G is the corresponding process variable. So from this structure clearly you can notice that C, the controller output, is going to be equal to U1 plus GGI by 1 plus GI, G minus GM, or minus U1. So it's a very simple block diagrammic representation. You can reduce the block diagram and you can obtain this particular expression quite comfortably. And then you can also notice that the denominator, if you look at the denominator of this, you can see there is a term called G minus GM. So the question that is before you is when this particular term will become 0, G minus GM. Can you think about that? Yeah, it's quite obvious that G, when the process model, when it is equal to the real-time process, okay? So then naturally G minus GM will become 0. So once this term vanishes, you're going to get G minus GI or minus U1. So that's this diagram in fact represents that. G into GI, okay? Or minus U1, and you can also see U1 is getting added up to get the corresponding process output. So naturally, if I'm going to choose GI is equal to 1 minus GM, what will happen here? If I'm going to choose GI is equal to 1 minus GM, for example, if I'm going to have a GM of 1 by tau s plus 1, GI will become tau s plus 1, and therefore GI is going to have a kind of a problem like a derivative control mode. Okay, so you have already learned that the derivative control mode is not sufficient for maintaining a controller performance. Do you know the reasons? I hope you can recall the reasons. Derivative control mode normally is going to aggravate the problem of high frequency noises. Apart from that, if the change in error is going to be equal to 0, naturally if the steady state error is going to be equal to 0, the derivative control action is going to take 0 control action. Okay, so then that's not preferred. So if I'm going to choose GI is equal to 1 by GM, it's going to give me a lot of trouble. Okay, so I need to devise some mechanisms so that I can avoid these kind of scenarios. So that's where the idea of the internal model control really comes into picture. Okay, so here you can see GM is equal to K by tau s plus 1, and GI is equal to 1 by GM is going to give me tau s plus 1 by K. But that's not what I'm looking for. I'm going to introduce deliberately a function like f of s equal to 1 by lambda s plus 1, which when added along with the GI can provide me a much better kind of control action, which is more like this. Okay, GC is equal to tau s plus 1 by K into lambda s plus 1. So this is the idea behind the internal model control. Maybe you can simulate this in a MATLAB Simulink environment, which I have been advocating for some time. Maybe you can see some of the results and try to submit your results in the Google Classroom forums. Maybe I'll go through it and get back to you. So those who are having any doubts, maybe you can post some questions on the Google Classroom. Myself and Dr. S. Venkatesh will try to clarify your doubts. Okay, thank you very much.